Hey guys, it's me, Wolf, back with not another Stronghold Crusader builds video. I would really like to continue with that series, but every time I was using my bandsaw, the flaws that it has just jumped right into my face and they were starting to seriously get on my nerves. I just didn't want to continue making uneven cuts while knowing that I can make some slight modifications and improve the outcome. So here we are in Can We Fix It Part 2, a series about me trying to improve my bandsaw with moderate success. I'm trying to keep this video at a reasonable length while still going really into detail. Obviously, there would be many more tinier details, but I'm trying to only mention some that I find important and that could maybe help you with your own projects. But not so fast, I have a little story to tell you first. We haven't even started. On the last Stronghold Crusader build, my bandsaw blade broke. And it didn't break at the welded seam, even though I thought that would be the weakest spot. But anyways, I've ordered 2 bandsaw blades from 2 different companies, only because I was impatient. One of them had a delivery time of 2 days and the other one had a delivery time of 4 days. So I took the first blade, set it up on the spinning wheel, adjusted the angle, beep bop boop, turned on the machine, and this is what happened. How weird is that? I checked the blade tension again and looked if I've ordered the correct size, but everything seemed to be right. 2 days later the other blade arrived and I tested out that one, hoping that only the blade was faulty and not the bandsaw. And it turns out it was the blade. Oof, dodged the bullet there, and you can go back where you came from. That's the end of the little story, and now we can start with the age-old problem of adjusting the blade on the upper wheel. I've already talked about this in the first part, but this time I tried to really understand how the machine functions. I've almost disassembled the entire bandsaw into its individual parts. I've removed the table, all the safety covers, the blade guides, and even the upper wheel. And this is what I found out. The upper wheel can be divided into 2 segments. I'm calling them the static part and the loose part. The principle I'm understanding here is that the static part is mounted on the casing at the right angle and the right height. The 2 parts are only connected with this metal bushing, so the loose part is, so to speak, hanging on the static part. The spinning wheel is attached to the loose part and the blade is basically pulling the lower and the upper wheel together. So in summary, that means that all parts need to be adjusted in a way so that the upper wheel is getting pulled at the right angle. But how do we do that and how does this work? The only connection from the static part to the casing is this plastic part and a screw. And you can already tell that it doesn't look that nice anymore. So the question arises, why was this made out of plastic in the first place? As far as I'm understanding, this screw should be tight enough to hold the entire contraption in place, but still loose enough so that this knob on the top can pull everything up to achieve the right blade tension. So I guess this part is made out of plastic so that the static part can still slide even though the screw is tightened. This screw technically shouldn't change anything about the angle of the wheel though. For that job we have 3 grub screws on the left and right side to adjust the pitch of the static part. The pitch is the rotation from side to side axis. The yaw on the other hand, which is the rotation on the vertical axis, can be adjusted by turning the knob on the back here, that simply pushes the loose part forward. All of this is sounding good, but here are the parts that I don't like about this. If I tighten the screw to the point where this whole contraption doesn't move left and right anymore, it is already too tight to be moved up and down to get the right blade tension, and leaving it loose is obviously not an option. Also, if I'm tightening the grub screws, adjusting the pitch, they are pushing themselves away from the casing, pulling the whole contraption forward, making this screw even tighter, and once again the wheel can't be moved up and down anymore. And the yaw of the wheel changes depending on the height of the entire contraption, because the screw stays in the same spot and the rest moves up and down, changing the angle again, and that messes up the previous adjustments. Now you're probably asking yourself, how do we solve that dilemma? And the answer is by not adjusting everything step by step, how you would normally do it, but adjust everything together. First of all, I removed the plastic part and used a brass washer instead, because as I've already said, in my opinion it doesn't make a difference anyways. Then I put the saw blade in place, approximately adjusted the wheel height and tightened the main mounting screw lightly. Our point of reference for the upper wheel is the lower wheel, because it is mounted directly to the motor and can't be adjusted in any way. So I grabbed a straight metal tube and held it against the two wheels. Then I started to adjust the grub screws back and forth together with the knob on the back to get the pitch and yaw of the spinning wheel right. Try to keep in mind that all the grub screws should be tight, or else they're gonna loosen up with the machine's vibration. Then when the angle was right, I slowly adjusted the blade tension while checking if the blade stays in the center of the wheel. The last step is to finally tighten the main screw and once again check if everything stayed at the right angle and the right position. Now we are done with the most technical part and the rest should be a little easier. Not really. Let's continue with the table. I've shown some steps on how to adjust the table in part 1, but there are still some things I'd like to improve. My main problems are that the table isn't completely flat and not at the right angle in relation to the saw blade. What I gotta mention before though is that this table is intended to be able to cut at up to 45 degrees, that means it has to be adjustable, and if we've learned something from the spinning wheel, we know that with adjustability comes tolerance. I've obviously started to disassemble everything again and started to measure if the frame where the table is screwed onto is flat. I used the spirit level and it turns out when the back is leveled, the front isn't anymore. First I thought this might be because of the paint, so I've sanded it smooth, but the paint wasn't the culprit here. My solution to this problem was a tiny bit of persuasion. And now I know that at least the frame is even. I mounted the table again and the blade seems to be perpendicular already. But just because the table is flat in the middle doesn't mean it is flat all the way around, so this precision is lost again when working with a longer workpiece. Here I've decided to put a 8mm thick piece of plywood onto the table. I clamped the metal tube to the side to use as a guide while cutting. Maybe you have already seen the gap here, but honestly I was focusing at the line while cutting so much that I didn't even notice it. And once I'm done, you can also see that the board I'm using just isn't perfectly straight. But in this case it doesn't make a difference, because the side of the board doesn't affect the blade in any way, so we can let that one slide. Then I drilled 4 holes on the board and countersunk them. Here a tiny tip: if you're using a drill press, make a hole in a scrap piece that has the same thickness as the board you're working with and slowly sink the hole step by step until the screw is completely flush. Then with that test hole adjust the maximum depth the drill press can go to then simply drill the 4 holes on the board without risking to go too deep. After that I simply clamped the board onto the table and used the holes as guides. By the way, I've left the cut on the board on the back so that it doesn't bother me while cutting. Obviously the downside here is that I have to remove it when changing the saw blade. I fastened the screws beneath the table with a washer and a locking nut because I don't want the screws to become loose over time with the vibration of the table. I turned the bandsaw on once to make some test cuts, and I thought that it might be smart to cut out a little more space around the saw blade, so if I'm too quick while cutting and it's forced from side to side, it doesn't rub on the side of the table. And last but not least, a little check again if the blade is still perpendicular. It's hard to see on camera, but I say it's a tiny bit off on the top here, but this tolerance is good enough for me. Okay, with that one out of the way, you might be thinking now, but Wolf, are you stupid? How are you going to use the miter slot now? You know, the one you've tried to fix in the last episode. But don't you worry, I am not going to use it at all. But I still need a sliding mechanism, so I came up with my own solution. The basic principle of the new slider is to use 2 L-shaped aluminium profiles and use them as rails to slide another aluminium tube between them. I could just attach them to the side of the table somehow and call it a day, but my brain doesn't function that way. That would be way too easy and not overly complicated, so my approach was a little different. I started off with cutting the rails and some square tubes to mount them onto. Something I wanted to show you is this new little measuring tool I've bought. I think it's really popular with carpenters and framers, and I'm using it because I had to make a line on every rail on the same distance, and you can just slide it in place, lock it with this little knob here and go at it. Really helpful. Another way to make a mark on aluminium would be to just use a steel caliper and make a light scratch. I've punched the 8 holes with the manliest hammer ever and used the drill press with a 3.3mm drill to make all the holes. Why 3.3mm, you're asking? Well, this is a European thing, but that's the core hole for an M4 screw. I've drilled them through both parts to perfectly line up the holes first. Then I drilled open the holes on the rails to 4mm so that the 4mm screw can fit through, and cut a thread into the metal tube below to screw the two pieces together. While doing that, I thought about how I would mount these two rails onto the base plate later, and decided to drill the two outer holes open to a 5mm hole to put the screw in there. Speaking of the base plate, I used the same material that I've used for the table and cut it on my bandsaw. How do I keep doing this? Next, I've clamped the first rail onto the board and drilled the holes through the bottom. Fixated it with two screws and used the tube I'm going to use as the slider as a spacer to make the other two holes. When mounting the slider to the bandsaw table, I had to make sure that the upper edge of the rail is slightly below the edge of the table, and for that I needed another spacer right here. Sadly, I didn't have more of the board I've used for the table, so I had to rummage around and pull out some scrap pieces, cut them into shape so that they look kind of good, and glue them onto the base plate. The next day I've arrived at the workshop and fell once again victim to the old craftsman irony of not finding something and then finding it. But the scrap pieces were also glued onto there tight, so I just rolled with it. Before mounting the slider to the table, I've made a test cut by using a 90-degree angle to check if the saw blade is perpendicular to the front of the table. I've made the cut in front of the line so I can see it better, and this seems to be okay. It got a little thinner towards the middle here, but that was probably caused by the blade drifting a bit. I've aligned the metal tube with my 90-degree angle to have a line of reference to align the slider to. Another tiny modification I had to do was drilling out two holes because on the underside of the table there are these two knobs. To transfer the holes onto the piece of wood, I've simply clamped it onto the table. I used this tool again to make sure that the slider is parallel to the metal tube I've clamped onto the table, and I made this line because the side of the wooden board wasn't parallel to the slider. I cut off this part and used these two holes to also mount the slider. At that point though, I didn't have screws long enough, so I had to continue a little bit without them. So in the meantime, let's continue with the actual sliding part, and I'm trying to keep this a little shorter. First I had to cut off a metal tube, and this is how I'm normally doing it, because I'm too bad at making a straight cut with my angle grinder. I'm marking the cut all the way around the tube with an angle and score the first side. Then I'm turning the tube and use the previous cut to start the next one. I do this 2 more times, and if I've done everything correctly, the last and the first cut should line up perfectly. With all 4 sides scored, it's easy to finish the cut all the way through. I had to screw 2 3D printed parts onto the tube. I've clamped it on there, made a mark where the holes are, and to make all of them in the right place, I've made the 3 in the middle first, then screwed the part on there, and then made the last 2. I'm using the angle measurement thingy from the old slider, and to attach it to the tube I used another 3D printed part where I've glued one of these welding nuts into. I slided this part into the tube and fastened it with super glue and 2 screws. I also added the lid on the other side. Now I had to cut a metric 8 threaded bar into 4 pieces, and rounding off the cuts is going to make the threads usable again. With thread glue I fixated a stop nut on the end of all the rods, then I added a 3D printed spacer, a ball bearing, another spacer and another stop nut at the end. Like this, the inner bearing ring sits tight between the 2 nuts and the outer ring is able to rotate freely. I did this 4 times and glued them onto the tube with the 3D printed parts. And at the end I screwed the second set of 3D printed parts on top. And we are left with this bulky boy that is able to roll. I gotta admit, this was a pretty complicated approach, but it was fun to make. In actuality, I was crying several times during this. For some reason I thought that metal bearings would roll better on metal, so I still wanted to add some sheet metal on the bottom of the slider. I simply countersunk the holes and fastened it onto the wood with flathead screws. Then I've placed the slider with the angle measurement thing inside, and it was wobbling a little bit at the beginning, but then I noticed that this rail here on the right was a little off, and then it was working Okay. On that day the screws also arrived, so I fastened everything and it is honestly looking pretty good. I also tried to make a stopper, but I didn't think that all the way through. I wanted it to stop like this, but if I have a workpiece on there, that doesn't work anymore, so I'm not really sure whether or not I'm going to use this one. Now, as a relaxation method in between, I wanted to make a simple part for once, and one thing I didn't like was that my vacuum cleaner hose doesn't fit into the bandsaw. For that I simply 3D printed an open cone and I accidentally used the wrong diameter. Fun! I actually wanted it to go over this part of the bandsaw, but I got lucky this time and I can just reverse it and it still works. Okay, back to business. There's still one thing missing and that is the blade guide together with the safety covers. Originally the blade guide consisted of these two metal cylinders just stopping the blade from going left to right and a ball bearing on the back that turns if the blade gets pushed too far back. I thought that this method isn't an elegant solution and the blade scratching against these metal parts would just weaken it over time, so I once again came up with my own solution. Do you recognize the pattern here? But before I begin I would like to make sure that I know what the blade guide is actually for. As far as my understanding goes, it is mostly important for cutting curves, because without it the blade could get caught in the back and get twisted, therefore making it impossible to make a good cut. So basically the blade guide just guides the blade. I am mostly making straight cuts and theoretically with a perfectly adjusted machine I shouldn't even need a blade guide for that. But in actuality there are always some reasons for the blade not to stay perfectly straight. It could be because of unequal thrust of the workpiece, irregularities in the workpiece, and on this particular bandsaw model I've noticed that the blade tends to move from side to side a little bit by its own, maybe because of the spinning wheel, maybe because of the irregular turning of the motor. What I'm trying to get across here is I would like this bandsaw to have a blade guide. There are different types of blade guides and the most common ones are block, disc and bearing guides. Block guides are similar to the ones that were previously on my bandsaw. They are made out of steel, ceramic or even hardwood and they simply stop the blade from twisting by being on each side with a little play in between them. The downside of these are that the blade wears down more quickly because of the friction they cause. Disc guides have more surface area than block guides and they turn with the blade if it touches them, reducing the friction a little bit. They are mostly useful when having broader bandsaw blades and that's where the increased surface area really matters. Last but not least are the bearing guides. They have the least amount of friction, but depending on the quality they can be quite noisy and wear out pretty fast. And they also don't have a lot of blade contact. I gotta be honest here, I just wanted to build something with ball bearings for once. That's also why I've made the slider the way it is, so bearing guide it is. I'm still using this part where all the previous parts were attached to, and the basic principle is that I want to use two ball bearings on each side of the blade to keep it centered. What's important here is that the bearings are only touching the back of the blade, because this new bandsaw blade here is a crosscut blade, which means the teeth are facing opposite directions and go out further than the flat part of the blade. My first thought was to let the bearings rotate together with the blade at all times, but without wearing the blade down too much. So I've used a piece of heat shrinking tube that I heated onto the bearing to kind of give it a rubber coating. Then I made this simple metal part with two metric 8 holes at the bottom and connected it with a second part that will later be mounted onto the bandsaw. I used two flathead screws as the bearing shaft here to keep this part as flat as possible on the front, and together with a spacer and a nut tightened it to the metal part. Let's make a quick little jump to the bandsaw again, because I still wanted to use the safety guards together with my new blade guide. Something I didn't like about them was the bendiness of this part, and I get that they were built that way originally to be able to remove the bandsaw blade, but I still wanted to make a connection piece. I've decided to use this flat metal strip again and asked it nicely for me to bend at a 90-degree angle. Then I attached it onto the safety guard, and even though this would just hold fine, I used a washer and a stop nut on the other side because I've learned that it is bad manners to let a bare screw poke out where it's visible. Back on the machine, I beautifully marked the holes on the second part, drilled it through and then struggled to attach it with screws because I forgotten to tap the holes on the back. But once I attached it correctly, it seemed to hold together nicely. I've removed this part again and made some tiny cuts on the safety guards, and I wasn't quite sure how to attach the bearing guide on there. I've decided to make 2 more 90-degree parts that can be attached with the safety guard screws, but I guess the easiest way to explain this is by showing it to you. I made 2 long holes here to be able to move this part later on, and once I've adjusted everything, it was time for a little test run. I'm not gonna lie, this sounds awful. That's why I've decided to cut off the rubber coating, and now the space between the bearings was too large, so I had to make long holes for the shaft. And once I've mounted and adjusted everything again, this is how it sounded. The last step are making some test cuts, and as soon as I started to cut, the right bearing starts to turn, meaning the blade is drifting to the right. Then I tried something else, cutting a long thin strip out of wood, and as soon as I started cutting, the left bearing was turning, meaning the blade is drifting to the left. Now, does this have to do something with the slider I've made? Or the angle of the fence that is really just a tube clamped onto the table? Or maybe the table itself? Or the new blade guide? I don't know anymore. I don't want to be highly philosophic right now, but there is a really famous quote of Socrates that states, "I know that I don't know anything, and apparently as soon as you know that,
the path to recognize the truth opens up for you."
But anyways, I think that the precision I've achieved with my modifications is better than the precision I got before, but I probably still have to adjust and remake a couple of parts to fulfill my expectations. I hope that you got at least something useful out of this video, and if not, I hope that you were at least a little entertained. Feel free to leave a comment down below, and as always, thanks for watching.